Okay. So look at this reaction. So here's an example of stoichiometry applied with molarity, or merged together. So this is how many grams of NaOH are needed to react with 2 liters of a 0.20 molar HCl solution. So I want you to take a moment just to yourself and think, how is this different from a previous stoichiometry problem you've seen? Because you've done lots of stoichiometry. And then how is it the same?
It's different because we're using molarity to find out mass.
Okay, we're using molarity to find out mass. Anything else that might be different that kind of with that? Are you normally given 2 numbers for the reactant, or for the A? No, normally. So here you have not just like 10 grams of HCl or 5 liters of HCl or this many particles of HCl. You have 2 different numbers that you have to deal with, a volume and a molarity. Okay, so how are they the same though? Same. Well, there's a balanced equation, Phoenix.
Yeah, like they give you like some values like liters.
Okay, they gave you some liters, but how is it? Yeah, go ahead, Alex.
I end up with the same stuff.
You end up with the same stuff, isn't it? Like, isn't there an A? There's a substance A and there's a substance B, right? You're still finding grams, right? You have a desired substance, NaOH, and you have a given substance, HCl. So that part's the same, all right? So thinking about stoichiometry and using molarity, in a way, it's the same, except for that you have a solution and you're given 2 values to try to figure out how to start your stoichiometry instead of 1. Right? Normally you just have grams, particles, volume of A, but here you have a volume and you have a molarity. So let's try to see how we're going to be able to use that and accomplish what we normally want to do in stoichiometry, which is find the amount of one of the other participants. So again, as always, we have a stoichiometry problem. We have an A and we have a B. So let's figure out how to write that in here. Well, normally what we would say is, well, HCl is A because that was what was given to me. And for HCl, I know that I have 2.0 liters. This is from the prompt, right? And I have 0.20 molar HCl. And then I want to know how many grams of sodium hydroxide that we need to go with this HCl, right? That's all the same, so this is my B. So I would say, diagnosing this, identifying my A and B, this is a solution of A to mass of B kind of stoichiometry problem. Instead of moles of A to mass of B, it's solution of A. Now, whenever you hear mass, whenever you see mass, what do you guys think of as far as the NaOH? Well, mole, but how do you get to mass? Molar mass. I'm trying to think conversion factors. But when you see a solution of A and you want to get to moles, you're thinking molarity times volume. Does that make sense? In other words, right, the molarity times the volume. When you have a solution of A, that's what you'd be thinking, because the first step in any stoichiometry problem is finding moles of A. How do you find moles of A? The molarity of A times the volume of A. Okay? Let's do it. So we're going to kind of set this up now that I kind of have the rudiments. So the molarity of HCl, 0.20 moles of HCl per liter. Okay. All right. And then I'm going to multiply that by the volume, 2.0 liters. I'm going to extend this. Now, what we'll say, looking at this, well, look, liters cancel. And that number, whatever that number is, well, it's 0.4. Isn't that how many moles of HCl I have? So now I have moles of A. Now I'm ready for the magic mole ratio, which in this case is 1:1. 1 mole of NaOH for 1 mole of HCl. And right now you have, looking at units, moles of HCl now cancel. And then you are going to have, what comes next is, you want mass of NaOH. So you need the molar mass, 39.98 grams of NaOH, if you figure it out, per 1 mole of NaOH. And I believe if you do the math, and it only has 2 sig figs, you get 16 grams of NaOH. If you think about how this would look in the lab, well, I'd have a beaker. Into that beaker, I will have poured 2 liters of 0.20 molar HCl. And then I would have to do what? Add, because NaOH was a solid here, right? I would have to weigh out 16 grams of that and then mix it up, and boom, I'd have my perfectly set up reaction, right? With the perfect amounts. So you see how you can use solution stoichiometry and how molarity times volume is the key, because that's how you get moles of A. So if we're good on that, let's look at example number 2. This one's a little different. It says how many liters of a 0.1 molar NaOH solution are needed to react with 2 liters of the 0.2 molar HCl. Not how many grams, but how many liters of a solution. Okay? So this kind of stoichiometry, if you think about it, what you know is that you have your 2.0 liters of HCl, and it's 0.20 molar. You know that you have 0.10 molar NaOH, but what you need to figure out is like how much of that to add. So if you look at the way I drew up on the beaker over here, I had my 2 liters of my 0.2 molar HCl, and what you're trying to figure out is, okay, so I have a 0.1 molar NaOH solution. You guys see what I'm trying to get at here? Like how much of this solution with this concentration do I need to add? You know what I mean? Does that make sense? Like you have your 2 liters here, but we don't have grams here. We don't have a solid NaOH. We have a solution of NaOH. So we need to know how many liters of that solution, how many milliliters or whatever, we have to add to my HCl to make it the perfect amount. Kind of think about this arrangement here, gentlemen. This is a solution of A to solution of B kind of stoichiometry problem. Whenever I think of solution of A and solution of B, I'm going to be thinking molarity times volume. Molarity times volume. In a way, molarity times volume is not really a conversion factor, but it's what you're going to use to manipulate your concentration and volume into a moles. Okay? So, like I said, when we see mass, we say molar mass. Particles, Avogadro, but with solution, we're thinking molarity times volume. Okay? So let's look at how would this be solved? Well, as always, you're going to identify your A and B. You're going to do the moles of A like we just learned in the first example. You're going to use the magic mole ratio as always. Right? Then you'll have moles of B, and you're going to use the equation that moles of B equals molarity times volume to find in this case, the volume. And I'll show you how to do that when we go through the solution. Okay? So the key again is you're going to have moles of B, right? And then if you want to find volume, wouldn't you divide by the molarity? Think about that, right? If I have moles of sodium hydroxide and I know the molarity and I want to find the volume, wouldn't I take that moles and divide by the molarity? Boom, I'm going to get the volume. So that's how it's going to shake out at the end. So let's go through the solution now. Okay, so we already know that HCl is my A, NaOH is my B. I know that I have 2.0 liters of 0.20 molar HCl. And I have 0.10 molar NaOH. And I need to know how many liters of this. So again, solution of A to solution of B. Well, We just learned I need to find moles of A. So I'm going to take my 0.20 moles of HCl per liter and multiply that by the 2.0 liters that I have, and then liters cancels. Notice that when it says molar up here, but notice when I plugged it into my picket fence, I broke out that unit moles per liter so we can do the canceling of units. Okay, now it's time for the mole ratio. 1 mole of NaOH over 1 mole of HCl. Now moles of HCl cancel, and I'm left with moles of B. Well, I have moles of B, and like I said, if I take the moles of B, using this equation, and I divide it by the molarity, oh, holy Moses, I know the molarity. It's 0.10. So I'm going to say if I divide by 0.10 moles of NaOH per liter, remember that kicks it up into the numerator, then moles of NaOH will cancel, and the answer is basically going to be, I think, 6.0. Isn't it? No, 4, sorry. 4.0 liters if you do the math, because the first part is 0.4 and you're dividing that by 0.1. So that's the idea. So let's scroll back up and look at our beaker. So what we're saying is, when I have my 2 liters of HCl with this concentration, I need to add 4 liters of this. That's a pretty big beaker. We don't own a beaker that large. All right? Does this make sense? Pretty good. All right. So why don't we try this one on your own? So I want you to figure out what's your A and what's your B. And let's get me to the solution of how many moles of NaCl. Okay, and my NaCl, when it formed, will be aqueous because we're already in solution, right? And it's going to make aqueous NaCl. But I just want to know how many moles, not the molarity, not the grams, how many moles of NaCl would be made from that much sodium phosphate. Okay, and pretend then we have enough calcium chloride to go with it. Okay, so I'll pause the video and let you guys work on that for a moment. Okay, so what do I know? So I want to know how many moles of NaCl. So that's my B. This is my A. I know that I have 3.15 liters of sodium phosphate, and it's 0.275 molar. Okay, so what's the first step? Find moles of A. How do I do that? Molarity times volume, yeah. 0.275 moles. I'm just going to say SP for sodium phosphate per liter. And I'm going to multiply that by the 3.15 liters. Okay, that's going to get me moles of sodium phosphate. I have a mole ratio here. 6 moles of NaCl for every 2 moles sodium phosphate. So right there, that's my answer. What did you guys get for a numerical answer? 2.60. That's right. To 3 sig figs, that would be 2.60 moles of NaCl. Good. What if we wanted to know, though? That's good. Great. What if we wanted to know, because this is a solution, what if we wanted to know what the concentration of NaCl was in that last solution? You know what I mean? You have some NaCl, you have this many moles dissolved in whatever volume, right? Okay, and so the question might be, what is the resulting concentration of NaCl? For that, you need to know the volume. Yeah. Okay, right, thank you, Ryan. So let's scroll down and look at part 2 of this question. So it says, now, if the final volume of the reaction mixture was 3.90 liters, so think about that. I started out with, on my beaker over here, with 3.15 liters. And if the total volume ends up at 3.90, then I must have added 0.75 liters of the calcium chloride. Doesn't matter the concentration because we're not worried about that. We're just pretending that that's enough. Okay, so we must have added 0.75 liters because the volume of my mixture went from 3.15 to 3.90 because both of these are solutions and we put them together. That causes an increase in the volume. So if the final volume of the reaction mixture was 3.90, what is the molarity of the NaCl? Well, we already figured out that we have 2.60 moles of NaCl. And now we know so that it was 3.90 liters. Yes? And that ends up being my molarity. 2.60 divided by 3.90 is 0.667 molar NaCl. So once the NaCl formed in here, gentlemen, right, in this whole volume, once that 2.6 moles was formed in that large volume of 3.9 liters, it would end up being a 0.667 molar NaCl solution. And so you see the way I did that. Could have done if I had asked you that up here. If I had asked you that up here, if I had told you that the final volume was 3.90 milliliters or liters, couldn't you have then taken this, which is moles of NaCl, right, and divided it by that 3.90 liters? And that because molarity times volume is moles, and molarity is going to be the moles divided by the volume then, right? And so this, you would get that same answer of 0.667 molar NaCl. Okay? That's pretty cool. So we kind of did it in this order, but at the end, when you have your moles of B, like I just showed you up above, you could take that moles of B, divide by the volume of B, and you end up getting the molarity. Okay? Okay, so let's look at limiting reactants. So in this case, it's a little different because instead of giving you the amount of one solution and asking you about the amount of another solution, I'm giving you the amount, the molarity and the volume of both solutions. So let's write down what we know. We know we want to know how many grams of NaCl, that's my B. I have 3.15 liters, and this is 0.275 molar for my sodium phosphate. And I have 2.0 liters of my calcium chloride, and it's 0.300 molar. Okay? Now the question is, which one of these is your A? Which one of these to use as your A is going to be whichever one is the limiting reactant. Correct? So remember when we found limiting reactant, what we ended up saying was, hey, let's use those starting amounts, find the number of moles of B it would form. Yes? Whichever one of those is the less number of moles of B identifies the limiting reactant, and you would use that moles to carry on and find the grams. Okay, so let's do this. So for the sodium phosphate, okay, I'm going to take its molarity of A times the volume of A, right? So 0.275 moles of sodium phosphate per liter times that 0.275 liters, right? And then we know that there are 6 moles of NaCl. So I'm finding moles of B using each reactant over the 2 moles sodium phosphate. Okay, I'm going to scroll down here so we can see. Okay. For my calcium chloride, what would I say? What would I write? 0.300 moles of calcium chloride per liter times the 2.00 liters, right? Okay. And then I have a different mole ratio. It's still 6 moles of NaCl, but it's per 3 moles of calcium chloride. And what was this? This was the 2.60, wasn't it? Right? That was, remember, we already did that one. How many moles is this other one? 0.6 times 2. It's 1.20 moles. Because it'd be 0.3 times 2 is 0.6 times 6 over 3 is times 2, 1.20 moles. So which one is the limiting reactant? Calcium chloride is the limiting reactant. So then I'm going to take this 0.120 moles, multiply it by the molar mass, 58.44 grams of NaCl per 1 mole. And you can see I kind of have the answer down there. 70.1 grams of NaCl. And that is it.